Right. So yeah, thanks for the opportunity to talk to you today. Indeed, it'll be about the inner detector trigger from ATLAS and Run2. That's what we call the trigger where we run the tracking, and then some developments that have gone in for Run3. So we'll start off with the design and performance of the ID trigger in Run2, and then go on to a few improvements that have been made for Run3, which is just starting, including the use of unconventional tracking for long-lived particle searches. And as mentioned, this is all for the ATLAS detector, where we're concerned mostly about the inner detectors. That's the tracking detectors surrounding the proton-proton collisions in the very center here. If we zoom in a little bit on here, so the inner detector is made up of 3 subsystems. We have 4 layers of pixels that's surrounded by 4 layers of strip detector. Each of those is a double layer. So we have 12 total silicon layers to work with. And then surrounding that is the transition radiation tracker, which is adding additional space points at large radii for the tracks. And our inner detector has acceptance out to a pseudo rapidity of 2.5. And it has this barrel end cap structure with a transition region around a pseudo rapidity of 1.3. So in terms of the whole ATLAS trigger, we have to reduce the rate of events from the LHC from 40 megahertz to something more manageable to store. And that happens in 2 steps on ATLAS. First, we have some very fast custom electronics that make a decision to reduce that rate to around 100 kilohertz. And this is based on only calorimeter and muon spectrometer information.
So I'm gonna interrupt you for a second. For some reason, there's a black box in your Zoom window.
Zoom thing.
Okay, that makes sense.
I don't know if I can. I don't know how to get rid of it.
Upper right hand, or yeah.
Maybe. I'll just stick it down here for now. And then...
Okay.
The bottom left corner, that's perfect.
Okay.
Cover the data. That's
how about the bottom left corner? Because we're covering the slide number now.
Good idea. Yeah, there we go.
Okay. Thank you.
Right. So that region around the muon spectrometer or calorimeter is what we call that region a region of interest, and that's passed on to our high-level software trigger, which runs with full detector information, offline-like tracking, and that spits out a rate of something like 1.2 kilohertz, for example, in 2018, and that's where the tracking runs that we'll be talking about today. So, overall, the running tracking the trigger is extremely important to the physics program of ATLAS. It allows us to find the events that we're interested in, as well as rejecting all of those that we don't want. And since it's running in with time constraints, it's designed with speed in mind, and especially efficiency with respect to offline tracking. It doesn't really matter if we reconstruct a track online that we're not going to find offline anyway. We can run it in 2 modes, either over the entire detector, which we call full scan, or in these regions of interest that I was just talking about around some signature. It's used in a lot of places. It's used for all of the lepton triggers, so electrons, muons, taos, as well as B-jets to do the displaced vertexing. If we want to do isolation around the leptons, we run tracking. And for Run3, we're planning to really expand the tracking by quite a bit and run it in all of our jet and missing transverse momentum signatures, which is a pretty big increase in terms of the amount of tracking that we'll run. Right, so to go back a little bit, transitioning from Run1 to Run2, the ID trigger was redesigned because we saw that the strategy from Run1 didn't scale very well to the pileups that we expected from Run2. So like in the top left here, the processing time was going to be just way too long at the pileups that we expect from Run2. This was partly because in Run1, the tracking ran in 2 stages. And this resulted in duplicating things like data preparation and pattern recognition, which can be somewhat slow. Now, the offline tracking itself as a whole is too slow to run in the trigger, but there are shared algorithms, and so the trigger benefits from things like software optimization, moving to 64-bit processing, new compilers, new libraries, etc. And so in the middle here, you can see the improvement in processing time per region of interest with all of these optimizations greatly reducing the tail in the processing time compared to before. And finally was updating that strategy from 1.1 to run tracking in a single pass. So we're not duplicating that time in doing the pattern recognition, for example. And in the top right, you see the reduction in processing time for that. That's not quite a factor of 3 on average compared to the Run-1 strategy. So altogether, a lot of nice improvements in terms of processing time. Now I just want to walk you through how we run the tracking. This starts off with the region of interest, which might be the whole detector if we're doing full scan tracking. And of course, we have to read out the silicon, cluster the hits, and then form space points to actually run the tracking on. Then we run what we call the fast track finder. So this is unique to the trigger. It's optimized to be quick and efficient. And this is where we do our seeding and track formation, so the pattern recognition, if you will. And we have an option to already make a decision based on this information if you want to try to reject the event early to save yourself some downstream processing time. Otherwise, we then run what we call precision tracking. And this is close to essentially offline-like tracking, and its job is to increase the purity of the tracks as well as the resolution. So it's not redoing the pattern recognition, it's seeded by the tracks from the fast track finder. And here we're running, for example, the offline ambiguity solver to remove ambiguity between tracks. And finally, those tracks are extrapolated from the silicon out into the TRT. And then, of course, you make your decision whether or not you want to save the event based on that information. So we can take a look at some example timing from the muon trigger. So in the top left, we start with data preparation. So this is clustering space and space point formation. This is quite fast, on average less than 10 milliseconds. Then we have the actual tracking. So for the fast track finder, that's takes on average about 40 milliseconds, but it does have a fairly long tail out to about 300. But then running the precision tracking on top of that is quite quick, just like 7 milliseconds. If we want to run isolation, that's actually fairly slow, on average more than 100 milliseconds, and that's because it's run in a very wide region of interest. So you have a lot more clusters to deal with. And then finally, that extension into the TRT is again pretty quick, on average less than 10 milliseconds. So if you sum up all of the means, it comes out to a little bit under 200 milliseconds. So overall, pretty quick, though not as quick as you've been hearing about running on GPUs and so forth. We can take a look at the performance for muons on the left, electrons on the right. On the top left here, this is the efficiency for muons versus momentum. And you can see that it's almost fully efficient with respect to offline tracks. The same is true for electrons on the top right. This is versus eta, and you can see that there's a little bit of a dip in efficiency near the transition region between the barrel end and cap, but it's a very small effect. On the bottom, instead, I'm showing you the resolutions. So for example, on the bottom left, moving from fast tracking in black to precision tracking in red, you see that we're improving the resolution of the electrons, which is what we want to do with this step. And then for electrons, it's a little bit more complicated. On the bottom right, this is versus the electron PT. So if you have, for example, a trigger with a fairly high threshold, say 26 GeV, and we're looking at tracks down at 5 GeV, this is a case where the electron has radiated quite a bit. And so the resolution is quite a bit worse there. Here, we're not running any special run recovery in the tracking. So one more thing, which is that to really optimize the CPU performance and efficiency, we can still run what you would call kind of a two-stage tracking. It's still in one pass, but you run the tracking twice in some sense. And this is we use for tau and BJet triggers. So the idea is that you first run fast tracking in a region of interest with the entire extent along the beam line or z-axis, like this dark purple wedge here. And this allows you to find the primary vertex or luminous region. So you can run a second pass where you have a very narrow region in Z, but much wider in eta and phi. So this allows you to run in a large eta and phi relatively quickly because you've shrunk the Z-axis. And so in the bottom right, you can see that by running these two steps of tracking in blue and red, it takes about 2/3 the time on average to the single stage in black with a much shorter tail. So it's a nice improvement in speed for these triggers. We can also take a look at the performance for Taos and B-jets. So on the top left here, this is looking at the resolution for tracks versus Tau track PT. Again, you see that the resolution improves nicely when moving from fast tracking to precision tracking. The bottom left is the efficiency for tracking in B-jets, which is, again, nearly fully efficient, except you also see here the tracking that's used for vertexing, which is a little bit lower efficiency because we have a fairly high momentum threshold on the track candidates. And if you cut on something early in the tracking that doesn't have a great resolution, it decreases your efficiency a little bit here. But for vertexing, we don't need that to be perfect. On the right, instead, I'm showing you the track multiplicity and B-jet triggers. So it's this sort of like looking at the purity of the tracks. In the top right, you have in black the fast tracking with a very long tail. And in red, this is after you run precision tracking, you see that it greatly reduces the tail, so it's increasing the purity of the tracks like we want it to. And compared to offline track multiplicity in the bottom, you can see that it's, much closer. So it's getting quite close to the purity in the offline tracks. One final thing that we do to optimize B-jet triggers, because they're really the most costly in terms of CPU resources, is that for these jetty events, you might have overlapping regions of interest, and we don't want to duplicate work in those overlapping regions. So they're merged together in what we call super ROIs. And then we run tracking all at once in that region together. We also cache the vertex position for the event, so we don't have to keep computing that. That's a relatively expensive step. But then the vertexing itself for B-jets or leptons is quite fast. So now I'd like to move on to improvements we've made for Run-3, keeping in mind that we plan to introduce a lot more full scan tracking for our jet and missing momentum signatures. And then finally, we'll wrap up with the use of unconventional tracking for LLP signatures. So full scan tracking is, of course, time consuming, so we really want to speed it up. And we can start from the very beginning, which is the seeding. So we start by forming triplets from pairs of hits, for example, those circled here. And as you get more and more pileup, of course, you have a large combinatorics problem that you have to deal with. And so the idea is to speed up tracking as a whole by rejecting bad seeds from the start, so you don't waste time processing them downstream. And to do this, we're going to make use of variables which have some separation power between hits, which will correctly be assigned to a track in black here versus those which aren't. And one example of that is the angle of this doublet off of the beamline or Z-axis. To do this, we trained a classifier on the width of the cluster in eta and this inclination angle. So on the top right, you can see the region which is predicted by the classifier to have the correct hit association, and you see it's kind of a band here. So that band gets turned into a lookup table so that we can very quickly evaluate if these doublets should be accepted or not. And then using this for a very, for a small decrease in efficiency, I think the operating point's 95%, we can reject something like 50% of the background here. So it's a nice reduction in the total number of seeds that we have to deal with. And as a result of this, it speeds up tracking by quite a bit, roughly a factor of 2. Most of the speed up, or well, the largest increase that you see is in the seed processing, but of course this impacts downstream because you don't have to spend time processing those seeds. And it has a pretty small loss of efficiency. You can see this in the top right. This is the efficiency versus the truth track eta. And you really just see a small difference at large pseudo rapidity. And this is also summarized in the table here, where it's about a 1% loss for about a two times speed up factor, which is robust for increasing pileup, which is of course important when we're running the full scan tracking. So a nice speed up there. We also do, we've also done some additional work, again in the seeding. And one of these is that instead of creating seeds mixed between the pixel and strip detector, we only create seeds between the pixel or strip detector. So this avoids seeds that are going across this fairly large gap between the last layer of the pixels and first layer of the strips. And this results in another roughly factor of 2 speed up in processing time. Again, for a small loss in efficiency, these red and black points show you with and without the mixed seeds, and you can see that the difference is less than 1%. And then finally, similar to what I was telling you about with the 2-stage tracking and restricting the size and Z of the region of interest, what we can do is, for full scan tracking, reduce the ROI size in Z. So this plot is showing you on the x-axis that size of the region of interest, along with some vertical lines showing you the beam width. And for the processing time in red, which falls off fairly quickly, compared to the efficiency in black, which is rolling up very slowly. So for a small loss in efficiency, we can cut out something like another 20 to 30% in processing time. So all of this adding up together is a large reduction in full scan tracking time, allowing us to run it much more often. So next, to wrap up, I would like to talk about how we're using unconventional tracking now. So there's been a lot of growing interest in long-lived particle searches for Run-3, and there are a lot of cool signatures you can look for. A lot of them rely on tracking information, so like displaced jets, trackless jets, things like that. But in Run2, we only ran standard tracking, and this was run out to about 5 to 10 millimeters, which really isn't viable for a lot of LLP signatures. And so we relied on calorimeter and muon spectrometer information for our triggers, and that resulted in generally high thresholds to keep the rates reasonable. And of course, this bites into your acceptance. So I'm going to tell you about 2 triggers that were developed, one for disappearing tracks and one for displaced leptons. So to start off with the disappearing tracks, this is for signatures like the top right, say something like a long-lived chargino, which passes through a few layers of your detector and then decays into something invisible and soft. So you're left, which you don't track, so you're left with this tracklet, which doesn't form a full track. And so what was done was to modify the tracking algorithm to save these tracklets that fail to become full tracks, which are run in full scan instances. So for example, missing transverse momentum triggers. These can be categorized based on the number of hits in, say, the pixel or SVT detectors. And a BDT was trained based on the various track quantities in order to try to reject background from combinatorics and other things compared to signal. So this plot showing you the BDT score here is comparing a signal from Monte Carlo versus background, which is just data from 2018. And you can see that there's a pretty good separation between the two. And this allows us, by using this, it allows us to lower the missing momentum threshold and the trigger that we're using compared to what we could do otherwise. So on the bottom right, this is the efficiency for the trigger versus the momentum of the Chargino system. And in green, this is what we would have by default, missing energy greater than 110 GeV. But by adding in the disappearing track trigger, we can improve the acceptance by something like a factor of 2 for these relatively low momentum systems. And so it's a nice example of how by being able to target exactly the signature we're looking for, we can really increase the acceptance by using tracking there. And then the final thing is making use of large radius tracking for the first time in the trigger. You already heard about this from Jackson earlier today, so I'm not going to repeat that part. But the key improvements we're making use of are the reduced number of fake tracks and the improved processing time. And as I was telling you before, in Run2, we had to rely on fairly high threshold triggers, something like 60 GeV for 2 objects. So if you have something like a displaced tau that you're looking for, say around 100 GeV, by the time that decays into an electron or muon, those leptons are going to have a transverse momentum less than 60 GeV most of the time. So you can't even trigger on the events that you want to find. And so this limited our acceptance to some interesting models in Run2. So now we're going to run large radius tracking for leptons in regions of interest using SCT only seeding to speed it up a bit, but then otherwise using the same selections that were optimized for the offline tracking, which is a bit of a tighter selection to reduce the fakes. Unlike the offline tracking, we're doing this in a single pass. It turns out that the performance in terms of efficiency and timing was good enough that we didn't need to complicate the algorithm by running 2 passes. And it's designed to run tracking down to 1 GeV for tracks with at least a little bit of displacement. So if we look in the bottom left here, this is the efficiency for muons versus the decay radius, so where the muon's produced. For standard tracking in green, which you can see falls off quite quickly, compared to large radius tracking in blue, which has a reasonable efficiency all the way up to 300 millimeters, which is the surface of the strip detector. In the middle here, this is the normalized processing time. So it's the processing time for the LRT algorithm and standard tracking normalized to the average of the standard tracking. So it's just showing you that on average, the LRT tracking is actually running quicker than standard tracking, which is nice. And the last thing I want to mention is that the efficiency for very displaced tracks depends a lot on the geometry of your region of interest and the number of hits you require. Because you can imagine if you have a very askew track like this in orange here, that eventually your hits will fall outside of your region of interest and you won't have enough hits to reconstruct the track in the first place. So there's a bit of optimization that you need to do in terms of computation time and your total efficiency. Now we can take a look a little bit more at the performance. Again, we're looking for electrons and muons with a displacement from a few millimeters out to 300. On the lower left here, this is the efficiency for electrons versus the offline track momentum. And you can see that we have a pretty good efficiency for momentum below that kind of 60 GeV threshold I mentioned before. This is also a single object trigger instead of 2, which is nice. So you can, for example, have 2 chances to fire it. So it's a large increase in acceptance for these low momentum electrons compared to before. On the right, this is for muons, and we're looking at the transverse impact parameter, T0. You can see the standard tracking in green, which goes out to 10 millimeters, and then outside of that, the large radius tracking takes over. So a nice complement there. And the last thing I want to mention is that we can also run full scan large radius tracking, which could be useful, for example, if you have a signature that doesn't have an obvious region of interest, or if you want to add large radius tracks to all of your jets. But it is a little bit slower because it has to run over the whole detector. There are a lot of seeds to deal with. So on average, it's actually about 1.7 times the time it takes to run the standard full scan tracking. And I should mention that this is run as a second pass after standard tracking, unlike the region of interest version. And in the lower left here, this is showing the efficiency for an R-hadron decay. So all of the tracks from either a muon or a quark versus their production radius. In gray, this is the offline reconstruction efficiency. And again, comparing in green, the standard tracking, which falls off quite quickly, and then blue, the LRT takes over. And there's a little bit of a difference between the online and offline reconstruction efficiency due to some optimizations that we put in order to speed up the processing time here. So like, for example, which seeds we keep and reject. Right. So to wrap up, so tracking in the trigger, right, is one of the most, well, it is the most computationally expensive part of the trigger. And so that requires us to be very clever about where and when we use it, but it's really a key part of the physics program, allowing us to find the events that we want to save. and showed you that it performed extremely well in Run2. And there's some cool improvements that have gone in for Run-3 that will allow us to expand both the standard traditional signatures like jets and missing transition momentum, as well as those for LLP signatures with unconventional tracking involved. So thanks.
Great, thank you very much. Any questions? Anybody from online?
No, not on Zoom anyway.
Okay, well, thank you very much for your talk. Probably we need some more coffee in the room, so we'll take our coffee break now. And again, thank you for being flexible about the timing.
Sure, yep.